Greetings and welcome to part 4 of this video module on the one-way analysis of variance. Within this module, we explore factors considered with the use of statistical testing for hypothesis testing, and in particular what we'll be focusing on here is the issues of committing two different types of errors within our statistical testing, namely type 1 and type 2 error. What the p-value, the significant levels of 0.01 or 0.05 may be telling us or not telling us, and then lastly the use of effect sizes. To begin, whenever we're using any sort of inferential statistic for hypothesis testing, when we're talking about hypothesis testing, we're talking about rejection or acceptance of the null hypothesis in favor of an alternative hypothesis. We generally rely on the probability value associated with obtaining a test statistic. Whenever you're learning about a t-test with a t-statistic and we had to see whether or not our t-value exceeded a certain critical value. On the previous module, we looked at the use of the f-statistic to make decisions around the acceptance or rejection of the null. Once we got our f-statistic from the variance component from the mean square, we could go and look into a probability distribution table using our between and within subjects degrees of freedom to identify a critical value to see whether or not our f-statistic exceeded that, in which case we'd accept or reject the null hypothesis. Whenever we're engaging in hypothesis testing using p-values, we want to be mindful of, what is it we can do to make sure we're making accurate and correct decisions. We certainly don't want to say, we've rejected the null, hence we find that this professional development program is going to be advantageous for teachers, counselors, students, whoever your target population is, and then start moving in towards making policy decisions, allocating resources, taking up time to start implementing professional development that may have or may not be effective just because we found that the p-value itself indicated significance. And generally when we're talking about significance, we use a 0.01 or 0.05 level. These tie directly into what we call type 1 and type 2 errors. So to begin here, we see we have a table here, and whenever we have, the rows, we see we have equal means. Whenever we have equal means, we see that the null hypothesis would be true, and then in the columns we have our decision. So for example, if we do have equal means where in the population our null hypothesis is true, that the groups just do not differ, if we make our first decision where we reject the null, this would be an incorrect decision. This would be an indication that we've committed a type 1 error, meaning that we said differences exist when in fact they do not. Okay, so in this case, we might say this professional development worked, this instructional strategy worked for students, this counseling method worked effectively for clients to help with PTSD symptoms or something. However, when in fact it's not effective, we've made an error, and this is what we'd call type 1 error. We're saying that the means differ when in fact they do not. However, if we retain the null, this would be a correct decision. Okay, so we want to be able to say if there is a true null, we want to accept it. We always want to have the correct decision, so we have to be mindful of what are the factors that are going to help us ensure that we are making the correct decisions throughout the design of our study and the analysis of the data. The second instance is where we have unequal means. In this case, the alternative hypothesis is true in the population. So if in fact our decision is to reject the null, as we see here in the lower left-hand part of the cells, that would be a correct decision. That's, the null should be, it's groups differ in the population, and hence we've reached that conclusion. That would be a correct decision. However, if we retain the null, this would be what we'd call a type 2 error, meaning that we've said that there's no group differences when in fact there are. Okay, and so we want to do the best we can to, make the correct decision, be mindful of type 1 errors where we don't want to falsely reject a true null, and we don't want to make a type 2 error where we accept a null that should be rejected. What are things that we can do to be mindful of this, and what are factors that what are practices that we could put in place to help us kind of make the correct decision? The first is our p-values. The p-values are the criteria by which we make decisions about rejecting or accepting the null. We have two significance levels that have just generally been used within practice. One is the 0.05, and this would be, we're willing to accept, 5 times out of 100 that the differences that we observe between the means is going to be due to just chance alone. We're willing to accept that level of error that could occur. The other approach is using a more conservative p-value, 0.01. In this case, we're willing to accept 1 time out of 100. The means are going to differ just due to chance alone, not due to some kind of meaningful effect of our intervention or whatever it is we are doing. And so obviously in this case, if we want to reduce the likelihood of making a type 1 error, we could use the more conservative p-value of 0.01 instead of 0.05, because the 0.01 is going to be more conservative, and our test statistic, there's going to be a higher critical value that must exceed to kind of say, we want to reduce that likelihood of making a type 1. But at the same time, we might be increasing our likelihood of a type 2. Another one is increasing sample size. And so increasing sample size reduces the error associated with committing a type 2 error. And so, and two, by increasing sample size, we have more what we'd call power to detect group mean differences, but also what we're doing is increasing the likelihood that our sample is going to be more representative of the larger population. And so these are just two approaches that can be used within the design of a study, and then also within the statistical analysis is our p-values and our sample size. So we do, generally within quantitative, within each group, we want to generally, as a rule of thumb, 30 people per group is kind of a general rule of thumb. Because their higher sample size can be more likely representative of the characteristics of individuals within the population. Importantly, what null hypothesis testing does and does not tell us. Just because we reject the null based off a p-value does not mean we have anything meaningful at hand. It just indicates statistically the means that we are comparing differ. There's much critique of using this approach, the p-values, to make decisions around group mean differences. Many people just say they shouldn't even be used. However, they are part of psychological educational research, and they are one tool for help us guide and understand our data. However, just like with anything, we must be critical of what it is we're doing to ensure that we understand what it is we're doing, why we're doing it, what these results are not telling us, and then where do we go moving forward, particularly with future research and guiding practical decisions here. So what these are some pointers derived from a website, Our Psychologist, a very informative website in terms of null hypothesis statistical testing. Some of the factors that it does not tell us is, one is that we do not know the probability of results being due to chance. We're just saying, if we use a 0.01 or 0.05, we're just willing to accept perhaps 5 or 1 time out of 100 that results are going to be due to chance, but we don't really know at hand that what's the likelihood of these results being due to chance. We just have our test statistic, and we're comparing that to a critical value. If we reject the null at 0.05, we're not 95% sure that the alternative hypothesis is true. Okay, we're just saying we're willing to accept 5 times out of 100 that the results just might be due to chance. We don't know. We can't say anything for certainty in terms of whether null or alternative is true. Likewise, if we reject the null at 0.05, the likelihood of a type 1 error is not just 5%. Again, we're just willing to accept 5 times out of 100 that this might be just due to chance, but we don't know the likelihood of committing a type 1 error. There's other factors that come into play. P-values do not tell us whether or not the results are important or not. Okay, it just might be the fact that we have sample size that are large enough, or maybe there's outliers there that would just kind of skew the data to the point where the results are statistically significant. That's all we are finding as if these are statistically different. It has nothing to do whether or not these results are clinically significant or practically significant. P-values do not tell us whether or not the results will be replicable. Okay, again, that there's so many other factors that come into play there, meaning that the context, characteristics of the participants, the fidelity of the implementation of the intervention, so on and so forth. There's other factors. The p-value is just telling us the likelihood of obtaining this test statistic. The p-values have nothing to do with treatment effects. Again, we're going to look at something what we call effect sizes that we must complement with p-values. If we have 80% power, this does not mean the probability is 20% that all is true. Again, the p-value is only just telling us whether or not the means differ or the same. One of the factors we want to consider is statistical power, and this is the ability to reject the true null hypothesis. And so one way to increase power is higher sample sizes and perhaps a lower p-value, and beta is the probability of not rejecting a false null. That's a type 2 error, but the probability of rejecting a false null is 1 minus beta. That's power, and we generally want to have a power value of 0.8. That's generally what you commonly see within practice. And so once we do obtain, for example, what we saw in our previous module, we found that the 3-group means were different. We had an F statistic of 7.41, which exceeded our critical value of 3.89. And so we did conclude that the 3-group means differ. However, what we need to do is go in and kind of compare, well, which of the 3 groups do differ. What we looked at in the previous modules, that we conducted an overall or an omnibus F test. So we at least know the 3-group means differ, but what we need to kind of dig into is which of the 3 groups do differ, and that's what we'd call like a post hoc comparison, which will be discussed. However, within this is what we want to always, whenever we find statistically significant results, we want to complement that with what we call an effect size. And an effect size is something that helps us characterize the magnitude of the difference between, in this case, the group means we're comparing. And we can get effect sizes for 2 estimates. One is for that omnibus F test, meaning that we got our F statistic and we got the p-value. We saw the p-value was less than 0.05. And so we can get, there's 2 estimates generally used within research in terms of the magnitude of the difference. One is omega squared. This would be the preferred estimate. There's a supplemental slides within the module that go through how to estimate this. And there's eta squared. Eta squared is what provided within many of the statistical software packages like SPSS. What these are telling us is these both range between 0 and 1, and what they indicate is the percent of variance in the dependent variable attributed back to the levels of the independent variable. So for example, if omega squared is 0.54, that means 54% of the variability in outcome scores is attributed to the different levels of the independent variable. Okay. Omega squared is generally preferred. It's more conservative than eta squared, so meaning that omega squared is going to be less than eta squared. And like I said, there's a supplemental module that will accompany this that has the formulas that you can calculate this. And generally we calculate these all by hand. But again, it's the percent of variance in the dependent variable scores attributed to the different levels of the IV. Once we conduct the omnibus test, we want to go and do pairwise comparisons to see, for example, is group 1 scores different than group 2 or group 1 different than group 3. We can conduct that statistical test through a post hoc comparison, or what we'd also call contrast comparisons. But the effect size for this is what we call Cohen's d. This should be something you should look for within any empirical study that's actually made statistical comparisons between groups. And Cohen's d is just looking at the differences between mean scores divided by standard deviation. So it's like a z-score. And it has 3 levels, in which will be further considered. This concludes part 4 of this video module.